So let's go ahead and get started this morning. It's good to see everybody. I hope everybody is doing well, feeling well out there. The goal for today is to start by proving the product rule and quotient rule. Well, not the quotient rule. It automatically follows from proving the product rule. But we're going to prove the product rule, and then we're going to do several examples that are a little bit different than just finding derivatives, which is what we've been doing all week, but it's related to that. And then if we have time toward the end, I'll introduce our next really important rule, which is chain rule. And we'll spend all of Monday's class going over chain rule. Now remember, the homework is not due till Monday night. So once we talk about chain rule after Monday's class, you should have everything you need to successfully complete that homework. But if you want to get an early start on it, there's several videos about chain rule that are up, and you can work on that over the weekend. So in regards to proving product rule, I want us to think about what the limit definition would look like, and then we're going to look at a sort of a geometric proof. I'm going to show you a figure that tells us how to handle it. So according to the limit definition of a derivative, if I try to take the derivative of f times g, this would be the limit as h goes to 0 of, remember, it's the function evaluated at x plus h. So this would be f of x plus h, g of x plus h, minus f of x, g of x, all over h. So this is what you would be looking at. And the problem with this particular limit is I have no idea algebraically how to simplify it. So I do not know how to simplify this limit. So we're going to have to do something a little bit more creative. CJ, you're asking about the skills quiz that's due. Is it due on Monday? Is it currently showing up as due on Monday? Okay, if it's currently showing up as due on Monday, then I'll move it to Wednesday, because I don't want you to have to do it until after we've talked about chain rule. So yeah, the skills quiz won't be due until Wednesday then, if that's the case. All right, so back to this. I don't know how to simplify this limit algebraically, but I have sort of a clever way to get around that. So I want to draw a rectangle here. It snapped as an arrow. There we go. And what I want to do with this rectangle is divide it up into pieces and then label those pieces. So I'm going to take this piece here and this piece here. Okay, so imagine that the piece here is some quantity which I'll call f of x. Then this represents extending that quantity by a little bit. So if I extend this quantity by a little bit such that now the entire length of the quantity is f of x plus h, then this little piece right here is f of x plus h minus f of x. The same thing can be done with the vertical quantity. If this first part is g of x and the whole thing is g of x plus h, then this little piece right here is g of x plus h minus g of x. So with that image in mind, can I use this to tell me how to simplify this piece right here? Because if you look at it and you separate it into areas, say I call this area A, I call this area B, and I call this area C, then it seems to me that this numerator that's up here, f of x, g of x, minus f of x plus h, g of x plus h, minus f of x, g of x, is the sum of these three areas. Because if you look at the area of the entire rectangle, it is f of x plus h times g of x plus h, which is this term right here. So the entire area of the rectangle is the first term. And then f of x times g of x is this big rectangle here. So if I take the entire rectangle and subtract off this little corner piece here, then that leaves these three areas, area A plus B plus C. So the way that we're going to handle this is I'm going to replace the numerator of that limit with the area of A plus the area of B plus the area of C divided by H, because that's what that numerator is equal to. So if you look here, the area of A is f of x plus h minus f of x times g of x. The area of B is f of x times g of x plus h minus g of x. And then finally, the area of C, let me give myself a little bit more room here. The area of C is, it's this little corner piece here. So it is f of x plus h minus f of x by g of x plus h minus g of x. So that has replaced each of those areas in the top. So area A is this, area B is this, and then finally area C of that rectangle is this. Now, it may not seem like we've made any inroads to making this thing easier to calculate, but we actually have. Because if you split this up into pieces, there's three pieces here, and I'm going to break the limit up into three pieces. This is the limit as h goes to 0 of, well, the first piece here is f of x plus h minus f of x divided by h times g of x. The second piece is g of x plus h minus g of x over h times f of x. And then the last piece is the one that's slightly more complicated, but it is the limit as h goes to 0, f of x plus h minus f of x over h times g of x plus h minus g of x. All right, so if you look at these one piece at a time, what you notice is that the limit here is going to ignore anything that doesn't have an h. So when I look at this first piece, the limit is just going to take the limit of the part in parentheses because that's the part that has an h, and it'll ignore the g of x. The same thing here, it'll take the limit of this piece and ignore the f of x. But here, this last limit, both pieces have h, so we're going to have to talk about that. But in the first piece, the limit of this thing, this is just f of x plus h minus f of x over h. That's just f prime. So this is nothing more than f prime times g of x for the limit of that first piece. And then if you look at the second piece, that is g prime. The limit of this is g prime times f. And then finally, for the last piece, clearly you can see that this is f prime. The limit as h goes to 0 of this, but the limit here has to distribute to both pieces. So the limit of this first piece is f prime, and we're left with the limit as h goes to 0 of this second piece, g of x plus h minus g of x. So it's simply a question of what does this last piece become, and as h goes to 0, you get g of x minus g of x, which is 0. So what you're left with are just the first two pieces, which are the product rule. So that's a neat little proof showing you that the derivative of a product of functions is given by the product rule correctly. And so the important geometric figure here is this rectangle that we use to prove it. It's actually a really classical result, and I thought y'all would enjoy taking a look at that. It's a little bit different way to prove that this particular limit is what we say it is in class. So now we've proved the product rule. It turns out quotient rule is, if you know the product rule, you can apply the product rule to a quotient, because you can think of the derivative of f divided by g as being the same thing as the derivative of f times the inverse of g. That's the same thing mathematically. So if you know that product rule is true, you can write every quotient as a product, and so you can achieve the rule for quotient rule by doing that, by applying product rule to this thing and showing that it gives the quotient rule result. So at this point, we've proven all the methods that we've looked at so far. The only one that we haven't proved is power rule, and that'll be coming next week. I'll prove power rule to you at that point. All right, let's do some Q&A. Let's answer some questions based on some things we talked about this week already. I just want to kind of see how we're doing. So we'll start with this first one. And as we go through this, if you have any questions, feel free to speak up or write something in chat. I hope everybody's doing well out there. All right, you have 1 minute remaining. All right. So the correct answers are -1/8. Let's take a look at it. So on this particular problem, this is a notational thing. I'm just making sure that we understand the notation of finding the derivative at a point. So suppose that your function is r equal 2 over square root theta. The notation r prime of 4 at dr d theta at theta equal to 4, these are the same things. This is the Newton notation, the Leibniz notation. It basically says take the derivative of this function, and then after you've taken the derivative, let's set theta equal to 4 to find the specific value. So we would be finding a slope at 4 for this function. Well, if you look at the function 2 over square root theta, this is the same thing as 2 theta to the -1/2. So this falls into power rule, which we talked about on Monday. So if I take the derivative of this function, the derivative of this would be 2 times the power comes down, and then you subtract 1 from the new power. So I'm just applying power rule there. So 2 times -1 would be -1 times theta to the -3/2. So remember, -3/2 is theta in the bottom number is 2, so it's a square root of theta cubed. So there's my derivative. Now I'm going to evaluate the derivative at 4, so I'm going to set theta equal to 4. And so 4 cubed is 64, and the square root of 64 is 8. So this is where the -1/8 is coming from on that problem. So as the course wears on, you're going to have to do this a lot. You're going to have to find the value of the derivative at a single point. And this is an example of that using power rule from early in the week. All right, let's take a look at another one. So these are just all applications of the derivative stuff that we've learned this week. So give this one a try. So where does this function have a horizontal tangent? This means where does this function have a slope of 0? That's what I'm asking you. Horizontal means slope of 0. Where does this function have a slope of 0? All right, you got another minute. All right, I think most of the responses are in. All right, the correct answer here is C, at 9/4. Let's talk about it. So I'm trying to figure out where this function has a slope of 0. So remember, the derivative measures slope. So I need to find, so we need to find where y prime, the derivative, is equal to 0. So I'm going to start by taking the derivative. Y is x minus 3x to the 1/2. So the derivative of that would be 1 minus 3 times 1/2. X to the 1/2 minus 1 would be negative 1/2. So that's the derivative using power rule. If I simplify it, this is 1 minus 3 over 2 square root x. So there's my derivative function. I want to figure out where the derivative is 0, so I'm going to set this equal to 0 and solve for x. If I do that, I will get, let's see, 1 is equal to 3 over 2 square root x. So square root x is equal to 3/2. Or if I square both sides, x is equal to 9/4. So if you look at the answer choices, answer choice C had x equal to 9/4. If you plug 9/4 back into the original function, you'll find that the corresponding y value is negative 9/4. So in fact, we know that the tangent line at the point x equal 9/4 is the horizontal line y equal minus 9/4. So that is the tangent line at that point. It turns out to be a horizontal line. So our ability to find tangent lines and analyze the slope of functions is gradually increasing in the course. We can do this faster and faster the better we get at taking derivatives. All right, let's try another one. So all of these are related to things that we've talked about during the week. So if you want to call this review, you can, but I'm trying to give you different questions than we had during the week just to kind of test how well you understand this. Some of the topics from the week.
One question, sir.
Yes.
So does that mean f at 89, or is that f to the 89th power?
It's neither. Remember, if we put it in parentheses, it's a derivative. So this means the 89th derivative of the function.
Oh, okay, thank you.
All right, I'll give you about another 30 seconds on this one. All right, so most of the answers are in, it looks like. And we are well, almost 100%. 90% correct. So negative sign is the correct answer. Let's take a look at it real quick. Remember, this is how sine, cosine, minus sine, and minus cosine, the derivatives are connected. I'm starting at cosine on the circle, and I'm going to travel 89 times. So 1, 2, 3, 4. Remember, any multiple of 4 brings you back to where you are. So if I said, what is the 89th derivative of cosine, which is what this question is asking, well, that's the same thing as taking 88 derivatives and then having one more derivative after that. But the key part about 88 derivatives is 88 is a multiple of 4. So if I do 88 derivatives of cosine, I've gone around this circle 22 times and nothing has happened. So I'm right back to where I started. So this is really just the same as saying the derivative of cosine, and the derivative of cosine is minus sine. So it's important to remember that if you take the derivative of these base trig functions 4 times, you get back to where you started. All right, not bad. Let's look at it. Next example. All right, so this one's a little bit different. You probably have a lot of these on the homework. I haven't done one like this in class yet, which is why I wanted to go over it with you. Suppose that I know particular values, like, I know the function value at different points. So I know f at 2 is 3. That's how you read this. So the function at 2 is 3, g at 2 is -2, the derivative of f at 2 is 5, and the derivative of g at 2 is -4. Using the information that's in this table, can you tell me what the derivative of f times g, right? So this is this is product rule, right? Can you tell me what the derivative of this product is at 2? So give you a second to think about that. So in case you were wondering what the notation here looks like, it looks like this. So finding the derivative of f times g at x equal to 2, that's the Leibniz way of writing that. And this is the Newton way. You look at the function f times g, the derivative of that evaluated at 2. So these two notations are interchangeable for this problem. All right, you've got another 20 seconds if you need it. All right, everybody that's logged in has responded. So the correct answer here is -22. -22. All right, let's take a look at it real quick. So the rule that we have here is going to be product rule. So the derivative of f times g is f prime times g plus f times g prime. That's just product rule. And the way that the evaluating it at x equal to 2 works is, well, you evaluate this at x equal to 2. So you're also going to evaluate this at x equal to 2, which means this will be f prime of 2, g of 2, plus f of 2, g prime of 2. And you should be able to look up all of those values from the table. So if you're looking at the table, let's see, f at 2 or f prime at 2 in the table is 5. G at 2 is -2. F at 2 is 3. And G prime is -4. So this gives me -10 minus 12, which is -22. So I want to look at a couple more examples from this. You should still have it up on your screen with the table. So I want to ask a couple more questions based on it, just to get you familiar with the notation here. What if I asked you, find the derivative of, 3f plus 2g, right, based on that table? If you were to do something like that, remember the derivative is linear, which means it distributes across addition and subtraction, and it factors out constants. So this is the same thing as 3f prime plus 2g prime. In other words, I take the derivative of f, which is f prime, I take the derivative of g, which is g prime. Now suppose I wanted to evaluate that at x equal to 3. Well, at x equal to 3, this would be 3f prime of 3, excuse me, plus 2g prime of 3. And so if you look at the table, f prime of 3 is 1/3, and g prime of 3 is -2, it appears. So 3 times 1/3 is 1, minus 4, you would get -3 based on the values given. So it's not just these kinds of questions. They aren't just limited to doing product rule or quotient rule or anything like that. You need to be able to handle the derivative of any function I give you by understanding how the derivative interacts with function notation. That really is the purpose of these examples. Because you don't have an actual function f of x or g of x to look at here, you simply just have values at certain points. It becomes important for you to know the formulas and how the derivative interacts with function notation. That's really what's being tested here. All right, so just to make sure that we're on the same page about that, let's do another one of these. So same table, I believe. Yeah, same table, but different question here. Now you're looking at f divided by g. All right, you got about another 30 seconds. All right, I just went in and changed the due date on that skills quiz, so it should be showing up as Wednesday now. All right. I suspect algebra may have gotten in the way a little bit here. I see several answers that are correct. They're just not written in a way that Learning Catalytics acknowledges that they're correct. You need to enter your answer. You need to enter your answer as a single fraction here. So if you entered an answer that was a combination of a bunch of stuff, do the arithmetic and simplify it. Enter it as a single fraction so you can get credit for it being correct. All right, so the responses that we have, the correct answer is 5/24. Technically, this answer is correct. The reason this answer didn't show up as correct is because it's technically 3 repeating. So you have 3 1/3 divided by 16. So you needed to write that as a single, like, proper fraction like this to get credit for it. But these are all correct. So what is that? 22, 55% of us had it right. All right, let's take a look at it. So once again, here are the notations for what we're doing. We're taking the derivative of f divided by g and evaluating it at 3. That's the Leibniz notation. The Newton notation is taking the function f divided by g, taking its derivative and evaluating that derivative function at 3. So our notation for this is, it's just going to be quotient rule. So if I apply quotient rule here, this is f prime g minus f g prime all over g squared. But I'm evaluating this at x equal to 3. So this is f prime 3 g of 3 minus f of 3 g prime of 3 over g of 3 squared. So if you look at the table values, let's see, f prime of 3 is 1/3, g of 3 is 4, f of 3 is 1, g prime of 3 is -2, and g of 3 is 4, so you have 4 squared in the denominator. So this is 4/3 plus 2 divided by 16, or 10/3 divided by 16, which is the same thing as 10/48. If you had entered 10/48, by the way, that would be counted correct. It knows that that's the same as 5/24, which is what you get if you take out a factor of 2 on the top and bottom there. So 5/24 is the correct answer. All right, so all of these kinds of problems where you have to take the value of the derivative at a single point, I usually have something like this on the exam because it's really important that you are able to manipulate the notations here to find the derivatives at a point. The ability to understand how the derivative interacts with function notation is really important. All right, we have 9 minutes remaining. So in the 9 minutes that are left, what I would like to do now is introduce to you the chain rule. Obviously, we're not going to have enough time to do enough problems, but I at least want to show you the rule. And this is one of those rules that there are several different ways to teach it. What I'm going to do is teach it what I think is the easiest way to understand for most students during class, and I'm not going to deviate from that. So I'm going to always explain it the same way in class. But if you go to the videos that I have online, some of the videos explain it slightly differently. So maybe if you're having a hard time understanding the rule from what we do in class, maybe the videos will explain it a little bit differently and that'll make better sense to you. But let's talk about the rule. I'll write down the formula for it in different notations, and then I'll do a couple of examples just so you can get used to it. So this is called chain rule. The chain rule is how do we take the derivative of the function f composed with g. Now, it may have been a while since you've talked about composition of functions. So let me remind you what this is. The notation here, f composed with g, is f with g of x inside of it. So you would evaluate g of x, and whatever comes out of g of x, you then plug into the function f and evaluate that. So you have two evaluations for this single function. This is the building blocks of most functions. Most functions are composite functions. For instance, if I looked at the function sine squared of x, that's the function sine of x sitting inside a square, which is the same thing as saying the outer function is x squared, and you've plugged sine into that function. So this is your outer function, and you've plugged g of x where x belongs. This is your inner function. So understanding what the outer and inner functions are for a composition is really, really important to being able to do this method consistently. So let's look at a couple of examples. I'll write down what the rule is. I'll do a couple of examples with you, and then we're going to do a ton of examples on Monday. So chain rule is the derivative of f composed with g is the derivative of the outer function with the inner plugged in times the derivative of the inner function. Oops. So that's the rule. It requires students to understand what the inner function is and what the outer function is for any composition that they look at. Because then what the rule says is you take the derivative of the outer with the inner plugged in and multiply by the derivative of the inner. So a quick example of this. What is the derivative of x squared plus 3 to the 7th power? So identify this. You should think of this as, this is how I want you all to think. You should think of this as the derivative of something raised to the 7th. Okay? So how do I take the derivative of something raised to the 7th power? Because x to the 7th is clearly the outer function here. Well, the derivative of anything raised to the 7th is 7 times that thing raised to the 6th. Right? Because that's power rule. Anything raised to the 7th is 7 times that thing raised to the 6th because you subtract 1 from the power. Well, chain rule says you take the derivative just like you normally would, but you keep g of x inside of it, but then you have to multiply by the derivative of the inside. So the inner function here is x squared plus 3. So this becomes x squared plus 3, but then I have to multiply by the inner derivative. The inner derivative is the derivative of x squared plus 3, which is 2x plus 0. So 7 times 2x is 14x, like so. So if I map this out for you, what you have here is the outer function is x to the 7th. That's the outer function for this problem. And what's been plugged into it, the inner function, is x squared plus 3. So the rule says take f prime, which is what we did here, and plug in g. And then multiply it by g prime. Okay, let's do another one. This will be the last one for today, or at least give you a glimpse of the rule. Take the derivative of e to the square root x. All right, if I think about that function for just a second, there's definitely a composition here. The outer function is e to the x. And g of x, the square root function, is what's being plugged into that. So the way that you get this function is by taking f and plugging in g. So that would be f, plug in g, and g is the square root function. So this is where e to the square root of x, this is how it's made. It has an outer shell and an inner shell, or outer function and an inner function. Chain rule says you take the derivative of the outer function first. Well, the outer function derivative is just e to the x. So e to the x, but you plug in the inner, but then you have to multiply by the derivative of the inner function. So this is e to the square root of x times 1 over 2 square root x. And that's your answer. If I was to break it down and diagram it for you a little bit better, maybe it would be helpful if I did this. You've got f of x is e to the x, g of x is square root of x. That means g prime is 1 over 2 square root x, and f prime is e to the x. So the rule says the derivative of f of g is f prime of g times g prime. Well, if you look at it here where I've made the substitutions, f prime with g plugged in, here's f prime. This is saying plug g into f prime. So we do that. That's e plug in g, and then you multiply by g prime. So we multiply by g prime. So what you're going to see me do in Monday's class, we're going to do a bunch more of these in Monday, is you're going to see me talk about what's the inner function, what's the outer function. You're going to see me make this little substitution here, f, g, f prime, g prime. And then we're going to substitute g into f prime, and then we're going to multiply by g prime each time we do this. What makes this particularly difficult is what if there are more than 2 functions involved? So what if you have f of g of h, right? So you've got 2 inner functions instead of just 1. So that's where a little bit of the difficulty is going to come from this topic. And we'll discuss a lot of that on Monday. But I wanted to give you a sneak peek of it. That way, if you wanted to get started on the homework a little bit, you're certainly welcome to. All right, y'all have a great weekend. I'll see you back on Monday. If you have any questions, let me know.
Quick question on the online homework.
Sure.
How do